Hello class, good morning. Rachel, Tristan, good morning to both of you. Sorry, I was muted. Hello, Rachel, Tristan, good morning to both of you. Okay. The chat is here. Okay, we are going to start just in a moment. I'm just setting up my second monitor. Can you hear me? Okay, thank you, Tristan. All right then. Yeah, so we are ready to start. So we are working with Unit 13. As a reminder, guiding note for Unit 13 and Unit 4 are available on Blackboard. You go to our classroom, then you go to guiding notes, and then you are going to see both 13 and 14 there. All right. So from the past 3 units, we were learning about two new functions or two new operators: exponential operators or exponential functions and logarithmic functions or logarithmic operators. So we were working with them in a very mathematical way, very theoretical way. We didn't apply those new function operators to real life problems. The purpose and the goal of Unit 13 is now to see two examples where these two functions of these two operators are used commonly. All right. We are talking about exponential growth and decay. And also, I should. I don't think this is the best title for the unit, but we will be going to use exponential functions and logarithmic functions. You will see how we are going to use them to work on two type of cases: economic or financial cases related more to interest, to loans, to future value. And we're going to be working with less population problems. Those are more related to biology. If you are into biology, in the biology field, you are planning to study for become a doctor in medicine, so this might interest you. If we all need to learn how to manage money, so it is a good idea. It is good to learn how the interests are calculated or how the future value is calculated. Okay, those two fields use exponential functions and logarithmic functions to solve real life problems related to them. Okay, so from the worksheet today, the first thing that you want to do is to memorize these formulas. Okay, so you need to memorize these formulas. We have three. The first two are related to financial situations. The third one is related to population or biology. All right. From the first two formulas, the formula that relate to financial, we have two formulas to calculate the interest, right? We have the compound and we have the continuously compounded. We are going to explore what they mean. Okay, before we go through why do we have two formulas for the financial situation, let's talk about the meaning of each variable here. Right? So we are seeing A, P, R, N, and T. What do they mean? So, yeah, I think you can see there. Maybe if I do a little bit more. All right, perfect. Okay, so what is the purpose of the formula? The purpose of this formula is to know how much money you will have, or how much money you will own after a certain amount of time. Okay, so the initial part here is the principal, the amount of money that was taken at the beginning of that period. So we call P the principal, right? So that is the initial value. Okay. R is representing the interest rate. Okay, the interest rate. T, and you see that I'm skipping A and N. I'm going to talk about them just in a moment. T, this is important because T is representing time. Okay, but careful here. When we are working with financial situations in this unit with these two formulas, the unit of time is year. Okay, that means that if you have a certain amount of time in an exercise and the unit of that time it is not in years, you need to do a conversion first. Okay, for example, if you have in the exercise 8 months, well, 8 months, how do you turn that into years? 8 divided by 12 is the same. It is what will give you 8 months in years. All right. We will do exercise about examples where we need to do this, so don't worry about that. All right. So A is the future value. But before going through A, let me talk about N. Okay, so we are going to talk about N, so I'm going to zoom here for a moment. Let's prove what this means. Okay, period of compound interest. We are going to represent that with the variable N. The meaning of this is that how many times in a year the interest will be calculated. Let's say, for example, that we have we take $10. Okay, we take $10, right? That will be our principal. Let's say, yeah, we make a loan for $10, right? And the interest is I don't know, 50%. So let's say that we have an interest of 50%. Okay, so that means that this interest will be calculated, okay, after a certain amount of time to know how much we own in interest. Okay, on top of the $10 that we own, we need to pay the interest. That's how the business works, right? So how many times this interest is going to be calculated in a year? Okay, depend of the period of the compound interest, depend of N. Okay, so if the period of the compound interest are annually, that means that N is equal to 1, and this is something that you want to know, okay, because we are going to be working with word problems and N is not going to be explicit given as N equal to 1. you need to read and you need to interpret the situation to know the value of n. So if you see that the period of compound interest, it is calculated one per time, or annually, it means that it is calculated one time per year. So that means that the value of n is equal 1. Okay? So if n is equal 1, it means that in this example, the interest will be calculated one time per year. All right? Semi-annually, it means every 6 months, so 2 periods per year. Okay? So n is equal to 2, and then it means that the interest will be calculated 2 times per year. Quarterly, and see that these are the most commonly periods used. Okay? So, but they might use a different period of time in a year in the exercise. Okay, so it is important that you know how to interpret it, the periods into the value for n in terms of the formula. All right. All right. So quarterly, every 3 months. Careful here, because every 3 months means 4 periods per year. So we have n equal 4. Okay. Monthly, every 12 every month, so that means 12 times per year. And daily, that means every day. And in financial scenarios, they consider a year to be 365. Okay, so you are seeing a pattern here that it means that we are increasing the value for n. Okay, the greater the n value, the number of how many, okay, the amount of time that the interest is calculated. Okay, so in turn, if we own money, we want our n to be very low. N equal 1 is the best scenario here if it's the case that we own money, because that means that the interest over the money that we own is going to be calculated just 1 in a year. But if on the contrary, if that interest will be calculated monthly, that means that the interest will increase, or the amount of money that we will own will increase 12 times every year, because every month 12 times in a year the interest will be calculated. Okay, so you're seeing a pattern here that n, if n increases, the amount of periods where the interest will be calculated, or the amount of time that where the interest will be calculated, will increase as well. All right. What happens if we get greedy, or the bank gets greedy and want to calculate the compound interest every 12 hours, every hour, every second? So the bank can do that, right? Because that is their business. Let's suppose that they, well, are going to calculate to the infinite. Okay? When the value of n gets greater and greater and greater, doesn't make too much sense, because we are living, the way we measure time is by seconds, milliseconds, seconds, minutes, hours, days, and so on, right? So it doesn't make sense to put like, well, I'm going to calculate your interest every second, every 2 seconds, right? But there is a way to calculate the interest infinite amount of time. Okay, and that's in terms of practically, this maybe doesn't make too much sense, but the mathematical properties allows us to calculate the interest to the infinite amount of time. The thing with that is that it doesn't make any much difference between calculating the interest for n equal 365 and for n equal to positive infinity. Okay, the details about this are not going to be covered in this class because it's not our purpose here. Okay, but you might see this relation, or you might explore these two values in a class that is more focused on financial situations. The thing is that when n goes to the infinity, or is equal to positive infinity, it means that now we are working with a continuously compounded interest formula. Okay, so that is the reason why we have two. Okay, if the person that is lending, I believe, the money gets greedy and wants to calculate the interest in a continuously manner, that person will be, or that institution will use this formula instead of the compounded interest formula. Okay, so that is why we have to. Okay, n is not equal to positive infinity, so n could be 1, 2, 3. On the higher value of n commonly used is when it is calculated daily, the interest is calculated daily. That means that n will be 365 days or 365. All right, but so in terms of our class, you want to look for compound or continuously compounded. Okay, those words are important because we are going to be reading through scenarios or problems where we need to calculate the interest. All right, and since we have two formulas, we need to be able to identify which formula we want to use depending on their scenarios. Well, if it's continuously compounded, then you will use the second formula. It is just compounded. It is compounded interest, or it is a how you say that? The interest calculated. Let's say in a compounded manner. Well, you use the first formula. All right. So we know why we have two now, and then so n will be the periods. N will be the period of compound interest, right? And A will be the future value, okay? Or the amount of value of the amount of money on or that you are going to gain if you are investing after a certain amount of time, right? So here we are using exponential, the exponential operations, and you can see that here. See that we have the exponents. Also, let me highlight here this here. Can I select the one I want? Yeah. All right. So you will see that now, when working with biology problems or the law of inhibited growth, we are seeing this formula. This formula is very similar to the one that we have here. Okay, and you see it, they're basically the same. The only thing that is that we change the notation of the variables or the variables. That way, in some way, the formula is telling you you are working with law of inhibited growth. All right. But A, see that A sub 0, it is in the place of B, so A will be the initial amount. See that now I'm not using the principal because we are not working with money. Okay, so now it will be the initial amount. K will be the growth factor, growth or decay factor. Okay, so why k is the growth and decay factor? If you can remember from the exponential functions, if the value of a is greater than 1, we have this shape for the graph. This is an increasing behavior. All right, when a is between 0 and 1, we have this shape, and this is a decreasing behavior. Okay, all right, so now how does this relate to the formula or the law of inhibited growth? So let me bring this here. Can you tell me the relation of the exponential function and the law of inhibited growth? Can you tell me how we can, how or why k is the growth of, is it the growth or decay factor? Can you tell me why, how this here applies to this, and how this property here allows us to determine if we have a growth or a decay situation? Can you see the relationship between a being greater than 1 and growth, and a between 0 and 1 and decay? All right, when k is greater than 0, okay, when k is greater than 0 means k is positive, it means that we have a growth scenario, growth situation. Why is that? You need to remember from the law of exponent, we know that e is a constant value, is 2 point something, is positive. Okay, so when k is positive, so let's focus just on the exponential part here. Well, this here, if we can see this exponential part as the following. Let me change colors. If we can see a of k, a raised to the power of k, e raised to the power of k, e raised to the power of k, e raised to the power of k. If we see that, that is going to be the base of the exponential expression, because t is the impulse, the function. Okay, so e raised to the power of k, it is the base of the exponential expression. So a equals e raised to the power of k. If a raised to the power of k and k is positive, it means that a is greater than 1. All right, so nothing happened there. But what happened if what happens if k is negative? So we are in decay. Decay. Let me double check that. Yeah, decay. So we are in a decay situation. Okay, let me put this here. But now, if k is negative, what will happen with e raised to the power of k? This is not explicit there, because you need to interpret it. Well, k is negative, that means that the exponent is negative. But what happens when the exponent is negative? So in this case, 1 over a, it will become a fraction. 1 over a e raised to the power of k, it is equal to 1 over a. Okay, so now a, the base here, well, a is still greater than 1 to be this between 0 and 1. So, but the point here now that I will use e instead of a. So e raised to the power of k is greater than 1, and now e raised to the power of k is between 0 and 1. Okay, so when the base is greater than 0, is greater than 1, we have an increasing behavior, and with e, or the base, e raised to the power of k is between 0 and 1, we have a decreasing behavior. Okay, and that's the reason why we have this formula here. It is used to determine growth or decay behavior, or to study or analyze growth and decay behaviors. All right? So let me go back here. Just a moment. Okay, so let's finish with this. So t is going to be time, but careful here, because t is not going to be necessarily be in years. Now, when we are working with the law of growth, inhibited growth, time could be any unit, okay? Not only years. And a of t, it will be the amount after t time, or maybe at t time. It is more specific, at t time. Okay, they will make more sense with the cases that we're going to see. Okay, all right, so I think we are ready to start working with the exercises. Any question before we begin? All right. So the mathematical concept here are not going to be so difficult, because from the past 3 units we were been dealing with exponential equations and with logarithmic equations. Okay, so here we are going to we are going to have mathematical problem more straightforward, but the most difficult part from unit 13 is to know how to read the word problems, how to interpret them, and know based on them how to collect the data that they are giving us and in which scenario we are working with. It will be a financial scenario. It will be if a financial scenario, would it be compounded interest or continuously compounded interest situation? if we are working with the law of unhealthy growth, are we working with growth or decay? Okay, those are the questions that you need to answer before starting working with the mathematical concepts or aspects of these problems. You need to be able to understand what the problem is giving to you, what the problem is, what is the goal that you're looking for in order to solve the exercise, okay, and how to reach that conclusion in a logical sense or a logical manner. So here you are going to use a lot of critical thinking. This is a good opportunity to start getting a picture of what you are going to do in your future when you are become a professional, or if you are already a professional. The reason why we are learning math. Why do we need to learn math? Well, all those mathematical knowledge are going to be in your background, right? And then what you are going to present on your work, how you are going to do your work, how you are going to solve situations in your work, is by using the applications of the mathematical knowledge that you have. In order to be sure or guarantee that your applications are correct, you need to have the knowledge. So that is the reason why you are studying math. Okay, that if you are in the path of a different profession that is not math, you are not going to be doing algebraic work. You are going to be solving real life situations, but you are going to use the algebraic work or the mathematical knowledge as a tool to solve those situations. Okay, so unit 13, it is important because you want to expand your critical thinking and how to apply the knowledge that you have as tools to solve real life problems. Right? So let's start, shall we? I don't know how well you can read. I will try to do my best to put this on I think that's the best I can do, but I'm going to start reading it. Okay. All right. So you have in your mind already. Well, we have two possible scenarios: a financial or a biology scenario. From the first phrase, the mass of a system. Okay, you want to be able to start picking up things from what you are reading. The mass of a system. What kind of a scenario is that? Is that a financial, or is this a biology scenario? What do you think from that part? The mass of a system. So bio. So now we know that we are going to be working with just one formula: A of t equal a sub 0 e raised to the power k t. Okay, that's the first thing that you're going to do. Now, the second phrase or the second part of this sentence, what is the word? Confirms that we are working with a biology scenario, continuously exponential growth model, and we know what is that. A of t equal a sub 0 e raised to the power k to t. Okay, being student in the lab. Okay, that doesn't say too much. All right, so the doubling or the double time is a term that it is used in this kind of scenarios, and you will see how this term of the double of time, it is used across the exercise that we have seen. Okay, so every time you see the double of time, okay, what does it mean? So let me zoom out just a little bit. What we know so far, we know that we are working with the law of unhealthy growth. All right. The double of time. What does it mean, the double of time? Okay. So the double of time, maybe the way I'm writing this, that it make not so much sense if we want to use it in a sentence, but remember this as a term, the term. Okay, the double of time, the meaning of this term means that if we have a as the initial value, a sub 0 is the initial value. So we know that from the workshop today. The double of time means that at t being the double time, okay, so t but being the double time, at that time what we are going to have, it will be the double of the initial value. Okay, let's see how this relates to our exercise. Let me continue reading here to present to you a more concrete example. So the double of time for this substance was observed to be 7 days. Okay, so now we know that the double of time, it is equal to 7. The double time, okay, is equal to 7. What is the meaning of double time? Well, the other sentence tells there were 58.7 milligrams of substance present at the beginning of the study. So let's take that apart. So we know that a sub 0 is 58.7. So at the beginning means day 0, and you are seeing that I'm using the unit day because the exercise is using days as the time for unit. So the day 0, okay, the beginning, in the day 0, the initial amount was 58.7 milligrams. Okay, so the day passes, and by the day number 7, double time, by day number 7, the double of time, okay, we have the double of the initial amount. So 2 times a sub 0 is equal to 2 times 58.7 milligrams. Okay, the value of t in day 0 is t equal to 0, and the value of t when double time is t equal to 7. Again, this is our days. All right. So from reading the word problem, we can get this information. This is the information that we got from this word problem. All right. Let me go further and let me complete the law of infinity growth, or the formula, okay, using the information that we got so far. So from that information, we can get that the formula for this problem is the following: a of t equal the initial time, which is 58.7 times e raised to the power of k times t. Okay. What I just did is just getting all the information out of the word problem. I don't know what the goal or what the question or what the problem is here right now. So let's read through the problems. Let t be the time in days since the beginning of the study, and let y be the amount of substance at time t. this means that the exercise is changing a of t for y. All right. Then we need to write a formula relating y and t. So we need to write the function relating the amount of substance relating in relation of time. Okay. So look what we are seeing here. We got the following expression. So there is something that it is missing. Let me put side by side the law of inhibited growth. This is an A. Okay. So we are missing two components. What are those two components of the that we are missing from the equation on the left? Well, we are missing the initial. We're missing the initial amount, and we are missing Rachel. We are missing K. T is there. So what we are missing is the initial amount and the growth decay factor. If we find those two, we solve the problem. Okay. So from the information that we got, let's see if we have those two. So far, we have the initial amount, 58.7. So it means that we need to find K. Okay, so let me put here A is 58.7, so that is the one that we got, and K is still unknown. At this point is where we are going to use the property of the exponential and logarithmic functions to find that value, the value of K. Since we are working with a double time problem, and double time, it is a common term used in this kind of exercises. I'm going to work with a sub 0 instead of 58.7 because that way I can give you a general representation on how to solve this kind of exercise. Okay, at the end of the step that I'm going to present, I'm going to go back and change a sub 0 to 58.7. Okay, but you are going to see that the step or the process that I'm going to present here, you are going to follow a similar step or process on all the exercises that are related to the double of time term. All right. Okay, so we are looking for K, but I'm going to change from 58.7 to a sub 0, a raised to the power of K, T. Okay, and the goal here is to solve for K. So maybe I should use a different color for K. What we know is that when T is equal 7, A of 7 or A of T is equal 2 times A sub 0. So we can use this information. How are we going to use this information? Let's substitute what we have. Okay, so if we take this and we substitute T for 7, so t now will be 7. And then that means, because t is 7, that means that the amount of substance that we are going to have when t is equal 7, it will be the double of the initial time. So the left side now is going to be changed by 2 times a sub 0. Does it make sense? Any question on what I just did here? All right. So look what happened here. I have on both sides of the equation the factor a sub 0. Okay, so that means if I can cancel them by just dividing both sides by a sub 0. If I divide both sides by a sub 0, I will be canceling that factor. And look what I got now. Can you tell me the type of exercise that we are going to be dealing here? Type of equation. What type of equation is this? Can you tell the type of equation that we are dealing here? What is the value or the variable that we are solving for? It is k. We are looking for k. K is in the exponent, hence this is an exponential equation. Okay, and we just work with differential equations. We solve exponential equations. The difference here is that now instead of k of the unknown variable being x, it is k. Let me show you how we are going to solve this. Since the variable is in the exponent, that means that we need to cancel the exponential operation on the exponential function here. To cancel the exponential function, we are going to use its inverse. Its inverse is the logarithmic function. The base of the exponential here is e. That's the base of the exponential function or the exponential operation. So that means that the inverse function that we are going to use is going to be log base e or natural log. Okay, so we are going to use natural log on both sides of let me set up this. Okay, so we use natural log on both sides of the equation, and then we are going to use what happened here. So on the left side, this is natural log of 2. So there is nothing to do there because this is just the representation of that value. By the way, it is an irrational value. But what happened on the right side? What will happen on the right side? What happened on the right side of the equation? What happened here? What goes here on the right side? think of the properties of the logarithmic functions. Think more specifically, think of the power property of the logarithmic function and think of natural log and e. 7 out in front. Okay. 7 and k. The entire exponent goes in front. Okay. So that way right now what we did is just we have brought down the unknown variable, the variable that we are solving for. See? So that's the first thing that we did. So here, I should like put this here. So here we use the power property to bring down the exponent in front as a factor. So now our variable is in a position where we can solve for. And since natural log of e, what's the value of that? Natural log of e. What happened with that? Log base e of e. What is the value of this? $2.7 is the value of e, but I want to know the value of log base e, or natural log of e. What happened here? What happened when the base of the logarithm is the same as the argument? It is 1. Remember that to answer the logarithmic function as what is the power of the base that equals the argument. So because natural log or log base e of e is equal 1, this here gets cancelled. Alright? In other words, that becomes 1. Okay? But 1 can omit 1 in a multiplication because it does not change anything. Right? So let me simplify this. Let me drop the parentheses. There now we don't need them. Right? So what will be, we are one step closer to the solution. What we need to do. What would you do to isolate k? I flip the places, but this, what is the step? What I'm asking you, what is the step between divide both sides 7? So natural log of 2 divided by 7 is the value of k. Alright. And you leave this as it is. Natural log of 2 is a rational number, so if the exercise is not asking you to round your answers, you are going to leave it at there. Okay? This is a not comfortable way to write a value, but this is just a value. Natural log of 2 divided by 7 is just a value. Okay, why we were doing this? Because we were looking for the value of k in the law of exponential uninhibited growth. Law of uninhibited growth. Okay, so now we are ready to complete the formula. Okay. And again, this is not going to look nice. because the value of k now, it is a fraction and k is on the exponent, and also k is being multiplied by t. So I will try to do my best. Let me change this by colors, so at least we can see by colors that. Okay, so this is the final expression. T is being multiplied by that fraction of natural log of 2 divided by 7. Okay. So how would you write that on Alex? So let me bring all this up. So let me put this here so you can see it. So on Alex, you are going to click on the boxes here. So on the first one, you're going to put 58.7. That's easy. On the second one, you're going to click here, and then you are going to be using the division symbol or the slash on your keyboard to see the fraction, and then just ln of 2 in the numerator and 7 goes below. Any question what we did here? All right. Now the second part of this exercise is how much will be present in 18 days. So now the exercise is giving us a exact value for t, and because now the formula is completed, the only thing that we need to do here is to plug in 18 into t. E natural log of 2 over 7 times 18. All right. So this is not too nice, right? Writing. So what I'm going to do is practice using your calculator to get this number. Okay, remember that here you want to round to the nearest 100. Okay, let's take a moment to practice how to enter this into your calculator. A crucial skill in this test will be how you enter the equations or the mathematical expression into your calculator. This is not so straightforward. Each calculator is different. So what I want you to do is to try to go to your calculator and give me a number. Let's see if you are doing this correct. Okay, I will calculate this also here on my end to see if we can get to the same answer both, right? So when you have an answer, let me know to compare your value with my value. Okay, do I have an answer? Okay, so let's check that. Okay, so let me change this for a moment. Move my face out of here. Okay. Can you can I don't know which type of calculator you have, but can you see the key with the letter E on your calculator, Rachel? Uh, okay, Tristan, you got 3. Okay, we will check that just in a moment. Okay, let me TI-34. Okay, TI-34 calculator layout. Richard, do you have? Hey, I want to see this. This is not working. Give me a moment. Open. Can I see us there? Okay. I don't know if this is going to work. Yeah. Rachel, is this your calculator layout? Okay. Where are we? Sorry, I'm just trying to look here. Okay, it means that we need to access to it in other way. So let me try. This is just staple. No, I want to call key E.
Alright, mathletes, this is a quick little video using a TI-34 multi-view calculator. If you're trying to figure out how to use the E button, this is how you do it. You're going to go ahead
Can
and
you
hit
hear
settings
the video?
and then log. And notice you have a log, you have 10 raised to some power. Let's scroll over and we're going to go to the Allen. And notice E is our second choice, so you scroll down. Choice 2, you can either hit 2 or scroll over and then hit enter. And that's what activates your E button. So now you just put your exponent. So say our exponent is 2, just type in 2 and then enter. And that's how you get to the E button. Alright, so hopefully that was helpful. I didn't see any YouTube videos out there that showed you how to do this, so hope.
Okay, so then you need to go to options. Did you get that, Rachel? Okay, so I send you the link of the video is there. Okay, if you can see it, just in a moment here, there. Okay, so I'm gonna try to put this expression into a scientific calculator, the scientific calculator that is built in Windows. Okay, so the way I do this is by first setting up let me see the exponent. In this calculator, I have the option to put e and raised to the power of 0. So what I'm going to do first is I'm going to set up natural log of 2 divided by 7 times 18. Okay, so t is 18. So what I'm going to do is natural log. No, I need to put first 2 natural log all this divided by 7, enter. So that is that's the value of natural log of 2 divided by 7. All that multiplying by 18. So that's my exponent. Okay, that's my exponent. Now I'm going to use that value as the exponent for e. So e raised to that value is what I got there, and then I'm going to multiply that by 58.7 and click enter. And now I got 348 9. So we need to round to the nearest tenth. Tenth is 2 decimal places. Okay, so Tristan, I think you got it right. We got it right. In mine, it's going to be different. On your calculator, Rachel, you want to first set up the E button with the exponent. Can you do that on your calculator? Okay, so if you are using the one on the phone, so the first thing, okay. So what I did is I depending on the calculator, but here I need to enter first 2 and then natural log. Then I divide it by 7. Okay, that's one factor in the exponent. Then I multiply by 18. And that is my complete exponent. Then I click on second to have this option, e raised to the power of x. X is the value that I have on the calculator, so I click there, and now I have e raised to that power. And then I need to multiply that by 58.7. Let me know if you got that number. Perfect. Okay. So I recommend to you that you practice how to use calculator when you are working in a test or a quiz. You are going to be stressed by the time left for completing the assessment. So on that time, if you panic, it is very easy to forget the correct step to get the right answer. Okay, then if you do that, you might put in a final answer that is incorrect. Make sure that you know how to use and how to set up your calculator in order to get the correct answer. Alex is going to be a very good uh, a very good practice for that, okay? Because Alex is going to give you real-time feedback on your answers, okay? All right. So second exercise, an initial population. Initial population. We're talking about a bio scenario. You want to know the key phrases. Okay. See that I am highlighting or making emphasis on the key phrases. Key phrases here are important because that way they are going to guide you through the correct scenario. Okay. Initial population. We're talking about fish. Fish confirm that we are talking about biology things or a biology scenario. The initial population is A sub 0 equal 510. Okay. The fish population growth according to the continuous exponential growth model. Second confirmation of that we are working on biology scenario. There are 918 fish in the lake after 12 years. Before going through the exercises or the questions, can you tell me if we are working with a grow or decay problem? Can you tell me if the growth factor is positive or negative from just what we just read? It is positive. Initial population means t equal to 0. A sub 0 is equal to 5, 10. T equal 12. A of 12 is 9, 18. Because we have an increasing, because the initial amount increases to 918. By this we know that we have K being positive. All right. So this is very similar to the one that we just did because we need to find two components of the formula. Y is being substituted by A of t. So I'm going to go quickly on this one. Okay, at this step, what we are looking for is the value of K. Okay, 510 is the initial amount. See that I'm not using A sub 0 because since we are not working with the double time, there's no way we can cancel the initial factor. Okay, so in this, if you're not working with the initial time, then you want to work with the number that you have from the exercise, right? So what we know that when t is equal to 12, we have 918 e raised to the power of k times 18. Okay, so our unknown variable is on the exponent, so this is an exponential equation. So here, the first thing that you want to do is to divide both by 510. Okay, you do that, and this is what we have. 918 divided by 510 equals e raised to the power of k times 18. Because k, the unknown variable, is on the exponent, we will use another logarithm to cancel the exponential operation here. natural log because the base of the exponential operation here is e. So again, this is not nice way to write numbers, but that's what we got. 9 divided by 918 divided by 510. We are going to get the natural log of that. And here on the right side, we got k times 18, dividing both sides by 18. See that I skipped some steps. Let me know if you have questions about those steps. Now k is equal natural log 918 510 divided by 510, all that divided by 18. I was using 18 is 12. Sorry, my bad. It is 12. Okay, I made a mistake. Then the number of the value of t is 12, not 18, but the process stayed the same. Why I was using that? The previous one was, I think. Okay. Again, you want to practice how to enter this on your calculator. So take a moment, enter the value, enter this into your calculator, tell me the value you are getting. Okay, I will do the same here to make sure that your answer and my answer are the same. By the way, the answer for A will be y equals all this, and then the value of k will be this. Not an expression to work with, but something that you need to learn how to calculate it. Okay, so what we are doing here is to make sure that the value of, you know how to enter these on your calculator. Okay, what we are doing is not part of the exercise. This is the answer of the exercise. So the first question, it is completed. That's the correct answer. I just want to make sure that you know how to enter this on your calculator. So I got k to be 0.04A9A. I believe I can stop there. Okay. Did you calculate the value? Did you evaluate the value of k? Did you get this answer?
So did you do
Mm-hmm.
9? Can you zoom in a little bit for me? Sorry, it's really hard to see. Did you do 918 divided by 510?
Yes.
18 divided by 510, which gave me 1.8, and then you divide that by 12?
Natural log first. Natural log of 1.8.
Which gave me 0.5877, and so on.
And then divided by 12.
Then divided by 12. Okay, I got it that time. So I just forgot to do the natural log.
Okay, perfect. That's good. Okay. But again, this is what I want you to do. You need to pay attention closely on how to enter natural log or how to evaluate this expression on your calculator. Okay, under the stress situation like the test or the quiz, this is going to get more complicated. Okay, all right. So the second question here is just getting how many fish are after 19 years. So it's very similar to the previous one. So I want to move to a different scenario or to a different exercise. Okay, I'm not going to do this one, but I'm going to point out key component here. Okay, I'm going to read the problem. The number of bacteria. So the number of bacteria, we're working with biology scenario. In a certain population increases according to the continuous exponential growth model. That's confirmation that we are working with the biology scenario. We a growth parameter. This is important. Growth parameter of 3.6%. Okay, when you see growth parameter, growth rate parameter, okay, in this exercise, the growth parameter is 3.6% per hour. Okay, how do you interpret this? So, well, K is 0.036. Okay, so K is positive, so we have an increase in behavior here. And the unit of time is in hours. Okay, from that phrase you get two things. You get the growth factor, and then you get the unit for time. How many hours does it take for the size of the sample to double? That's a very important question, and this is a very important exercise. Let me see if we got that from the first one. All right, so this exercise is very similar to the one that we did. So I believe I should do it, because even though it is this, you will do the same process, it's kind of different because now it's asking for time. Okay, so how many hours does it take? This means that the unknown variable now is going to be t. So we are going to find the value of time, and again you will see it take how many hours does it take for the size of the sample to double. So that means that we are working with a double time exercise. And again, double time term, I'm using it freely. I'm just using it to identify a specific type of exercise. Okay, so what we need to do here. So let's start with the formula. It is interesting here that we do not know the initial amount, but that's not a problem because we know that by the double time, and again, this is a term that I'm using freely just to specify the type of exercise, we know that we are going to have 2 times initial value, the initial value a sub 0, equals k. K is going to be 0.036 and t, and we are looking for t because t here is the unknown variable. The double time gives us the opportunity to eliminate the initial amount factor on both sides of the equation. See that with the double time, 2 times a sub 0, now we eliminate the initial amount from both sides, and this is what we got. Okay, so this part is very similar to the one that we did at the beginning. The only difference is that instead of looking for k, we're looking for t. So natural log on both sides brings 0.036 times t. So t equals natural log of 2, all this 0 divided by 0.036. Okay. The exercise has an specification that we do not round intermediate computation, but we do round the final answer to the nearest hundredth, 3 decimal places. Sorry, 3 or 2? Hundredths. Hundreds are 2 zeros. Hundreds are 2 decimal places. 10 is 1 decimal place. Sorry, I was confused about that. Okay, again, the problem is how to enter this into our calculator. So I will do that. 2 natural log, all that divided by 0.0036. That gives me a value of time of 19.25 hours. And that's the answer. Let me show you the written word. That's the written word. Okay. Any question here? Right? We were talking about the same exercise here. So I have more exercises here that are basically the same type of exercise, just with different numbers. So I'm going to skip those. Let me see this. This is just to create the function. Okay. Here we have a different type of exercise where we are working with financial. This is a financial problem. All right. So let's start reading. Chen deposited. Okay, deposited. That is telling you, well, we're talking about financial exercise. Deposited 7,000 into an account. Okay, deposited 7,000 into an account. This sounds to be the principal, but we don't have confirmation yet. Okay. Into account of 4.2% of annual interest rate. It's all this. So R is equal in the decimal representation, right? We take R as a decimal in decimal representation, so R is equal to 0.042. Okay. Compounded monthly. From here we have, so from the interest rate, yes, we have confirmation that the principal, we have confirmation that now this is going to be the principal. Okay, I'm going to put this just in a moment. Okay, so that's the principal. Okay, so we have compounded monthly. Remember that we have two formulas for the financial problems. We have the compounded interest and we have the continuously compounded interest. Compounded monthly, this is telling us that we are dealing with the first formula. The first formula is, I'm going to write it here. I know this is T. I think this is N. R. N. If my memory is correct, that's the formula. Yeah. Okay. That's the, so compounded monthly tell us that this is the formula that we are going to be using. For compounded monthly, also we can get the value of n. What is the value of n? Compounded monthly. What would be the value of n? Excuse me. It is 12. Okay, assuming that now we draw our main, how long, so that means that now the question is about time. We need the unknown variable is going to be t. How long it will take for this method to grow to 7,910. So that is the future value. All right. So let me put here the information that we got. So the formula that we are going to be using is the compounded interest the unknown variable is t. We got that the principal is 7,000, that the interest is 0.042, that the value of n is 12. Okay, and the unknown variable, like I mentioned, is t. Okay. So let me see if it would be wise to substitute these values now or now. Let me see. Okay. So this one will require a little bit of algebraic work or algebra work. So I'm not going to substitute those values yet. I'm going to be working with the variables. I'm going to isolate t, and then after doing that, I will substitute the value that we have to get the value of t. Okay, so our goal is to isolate t. First thing that I will do is I have an exponential expression on the right side, but that exponential expression is being multiplied by the factor of p. So I will divide both sides by p. I cancel here, and now I have a over p equals 1 plus r divided by n times t. Okay, so now t is in the exponent, so I need to bring t in the level where we can solve for it, right? So I have an exponential expression on the right side. The base of that exponential expression is 1 plus r divided by n. I'm not going to use log base of 1 times r divided by n. I'm going to use either log base 10, which is the commonly used logarithmic function, or natural log. In this case, I'm going to use log base 10, just to change things a little bit. So log base 10 is the same as just log. I can omit the value of 10. Okay. So the writing here is getting clunky. It's getting not nice. So careful when you are writing each step here. So this exponent belongs to the base or the argument of the logarithmic function. Okay. So the exponent completely goes in front of the logarithmic function. This whole thing here, let me change this in the color of this. That's just a value, okay? That's just a factor. It is a weird way to write a factor, but it's just a factor, okay? So that means that we are going to divide both sides. In order to isolate t, we are going to divide by n, and also we are going to divide by log base 10 of 1 plus r over n. Let me change the color of that. Let me copy and paste that. Oops. Okay, so I did that on both sides. That way I cancel this with this, I cancel this with this. And the equation for t will be t equals this. All right, so that is the equation for t. Now what we want to do is to substitute the value that we have for a, p, and n and r. Why did I choose to work with the variables rather than the numbers? I found, for me, I find more difficult if I need to do this step to isolate t. I find more difficult to work with the number rather than with the variables. That's why I choose to not substitute the values until I have t isolated, or I have an equation for t. Okay, so now what I need to do is just to substitute these values. Into that expression. Okay. Okay. So it would be t equal log. Oh, I missed one a. So a is 7, 9, 10. So these are the values for the variables. So it will be 7, 9, 10 divided by 7,000 times, divided by 12 times log 1 plus 0.042 divided by 12. Okay, and this is another expression that we are going to practice. Okay, so take out your calculator, start working with this, try to get a number. I will do the same on my end, and again, just to make sure to know how we are going to do this. you can't, I believe you can't, you are not going to run intermediate computations. That means that you will likely do all this in just one iteration in your calculator. Okay, you are not going to write down anything until you get the final answer, because if you write down something, if you have uh, decimal representation, you are going to round your answer. Okay, because if you have decimal a number values that are irrational, there's no way you can write all those decimal places. Okay, so in your calculator, you want to enter this, what we are seeing here, correctly on your calculator to get the final answer. The final answer is the one that you are going to round. You're going to round to the nearest hundredth, to decimal places. Okay, so this one is not easy to put on your calculator. So let me put this here. How can I talk this? No, I don't want this. Right. Okay, so I will start with this. The first thing that I will do, the fraction, then I'm going to add to that fraction 1, then I will do log, then I will divide by 12. Alright, so I will start with the denominator. Once I do the denominator, I will do the reciprocal of what I just did on the calculator to get the value of the denominator. You will see how I do that. And then lastly, I will do this division. And then the last log. The last log and then the division. That's not a good color. Alright, so we start. I'm starting with the 0.042 divided by 12. 0.042 divided by 12. 0.0035 plus 1 log times 12. So that whole value is what I have on the denominator. Let me change this. Right? So how do I make this value into the denominator? I have a key here, 1 over x. That gives me the reciprocal of the value that is in the screen of the calculator. So 1 over x, that is the reciprocal. So right now what we are seeing here is the denominator. 1 over 12 times log of 1 plus 0.042 divided by 12. All right. So how am I going to add the denominator to do the division? I'm going to multiply, okay? You can remember that 1, we can separate this. This fraction could be separated as 1 over the denominator times the numerator. Okay? So we got this. That's what I see here on my screen is the first part of that multiplication. Okay. Now I'm going to multiply by, so here I'm going to open two sets of parentheses. Okay, again, this is not easy. This is something that you want to practice. Maybe you want to find your own method that will help you to do this correctly. But I'm going to open two sets of parentheses. The first parenthesis is for the entire log expression. The second parenthesis is going to be for the argument. I'm going to do the argument first, and then I'm going to click on log. That is how my calculator, the calculator that I have here on window, works. Okay, you need to enter first the argument and then the logarithm function. So 1, 2, 7, 9, 10 divided by 7,000, close parenthesis. That is the argument. Then log of that, closing parenthesis, and equal. And that is my value. So I did this, and all this, remember that I need to round to the nearest hundred, so that means 2 decimal places. So this is 2.92, and what is the unit here? We are working with financial problem, so years. Okay, so tell me if you have any question of this. Okay, this is something that you want to practice. It is not an easy expression to put on the calculator. Okay, so this step here is critical, how to enter this on your calculator. Any question with this one? Okay, so let's move to the next one. Okay, in this one, this exercise, okay, so the number of milligrams bio of a certain drug confirmed that we are working with a biology biology scenario or biology problem. This is the number of patient the number of milligram. The number of milligram is represented by D of H of a certain drug that is in a patient's bloodstream. H hours, so times is represented by T by M by H. Okay, H is representing T, or is replaced by it is replaced or replaced T. Hours is the unit of time that we are working with. After the drug is injected, is given by the following function. So you can see this, that this is a function of the law, or this is the law of uninhibited growth, where K, the value of K is negative 0.4. This means that this is a decay problem. Okay. when the number of milligrams reaches 17, the drug is to be injected again. How much time is needed between injections? From the formula here, 30, we are seeing that the initial amount is 30 milligrams. Okay? So the question, reading the question is important because it's not like too clear what we need to do here initially. When the number of milligram reaches 17, if we are in a decay situation, it means that, that means that the age is going to be 17. So the amount at a specific time. The drug is to be injected again. How much time is needed between injection? So how much time is needed between injection here is asking for the value of age when d of age is 17. Okay, from the information that we have, we can start working with this. So 17 is on the left side, 30 e negative 0.4, all this times age. Age is the known variable here. And this, you want to solve this the same way we have solved the previous one. Divide both sides by 30. Natural log to cancel the exponential expression. So we have natural log of 17 divided by 30, negative 0.4 times age. You divide both sides by negative 0.4 to get age. Okay, and then what you need to do is to round your own answer to the nearest tenth. Okay, so you're gonna leave it there. This is the written work of the exercise. The next step that you need to do is to use your calculator to calculate that value. Okay, any question? Wait, were you? I think you were not seeing everything. I don't know. Let me change to this. Okay. In this exercise, it is interesting because I'm going to focus on the second part. So this is the formula that we have. Okay, and then we need to determine if this is growth or decay. So the way you can do this is by comparing this formula, because this is a biology problem, with the law of inhibited growth and decay, or inhibited growth. Okay, the initial amount is 420. How do I know that the initial amount is 420 if this formula is different? When you put t equal to 0, p of t is equal 420, because when t is equal to 0, the entire exponential expression gets cancelled, and what is left is just the factor of 420. Right? So now that we know the initial amount, we want to compare this expression and this expression, with the difference that now I'm going to use 420 for a sub 0. So 420 times e times k times e raised to the power of k times t equals 420 1.13 t. So we can cancel and then solve for k here. But if you look closely, if of k, it is represented by 1.13. 1.13 is greater than 1. Okay, it means that e of k is greater than 1. Hence, we are in a growth exercise or situation, because k is going to be positive. If k is negative, then e of k, if raised to the power of k, it will be less than 1. But e raised to the power of k is greater than 1, is 1.13. So that's a growth. Okay. To answer the last question, then you need to solve for k. Okay, but I'm not going to do that here. It is the same process. Cancel both sides for 20. Use the natural log to cancel the exponential expressions. Okay. Next exercise, how much should be invested? So we're talking about a financial problem. Now, at an interest rate of 7% per year, so 0.07, compoundly continuously tell us that the formula that we are going to use is going to be A, B times E, R times T. To have 2,500, so that is the future value in 3 years when t is equal to 3. So the unknown variable here is the principal. So I'm going to use this formula. I'm going to isolate first for p, and then I'm going to substitute everything. Okay, so this is the formula, step number 1. To isolate for p, the only thing I need to do is just to divide both sides by e over e raised to the power of r times t. So I have p here, a e r t, and then I substitute the values that we have. So 2,500 over e times 0.07 times 3. E raised to the power 0.007 times 3. Okay, and the rest is just to solve the exercise. okay? The last exercise that we are going to discuss is that few exercises are going to give you a different formula, different from the two that are in the worksheet of the day. If that's the case, then you need to use the formula that the exercise is given to you. Let's read through this one. A species of animal is discovered on an island. So we know that we're working with a biology problem. Suppose that the population size, P of t, so they are using P of t to talk about the population size of the species can be modeled by the following function, where t is measured in years. This is the following function. This is the function that we need to use to solve this exercise. Find initial population size of the species and the population after 8 years. Okay, so that this kind of exercise might throw you off a little bit because, well, what formula am I going to use? And that's part of the exercise. They challenge you to use a different formula. Okay, this is a specific formula that relates only to this exercise. Okay, if there's no formula given whatsoever, you use the formula that are on the worksheet of the day. All right. So how are we going to find the population size of using this formula? You need to remember that when we are talking about population, in each population size, the value of t is going to be 0. Then the value for the population size after 8 years, the value of t is going to be 8. So let's calculate the population size, the initial population size. So the initial population size is when t is equal 0. So p of 0 equal 450, all this 1 plus 3e raised to the power of 0.29 times 0. And that's the important part here, because that 0 makes the entire exponent equal to 0. So e raised to the power of 0, that's just 1. Three times 1. So it means 450 over 4, and that's the amount, the initial amount. Do we need to round? Let me see. Round your answer to the nearest whole number. Whole number. So we do this division. So it would be the whole number, so it would be 113. And that's how you get the initial population size. For the population after 8 years, you will do the same, but the only thing is that instead of 0, you're going to substitute 8 into t. Okay, I'm not going to do that one because it's the same process. Just make sure that you do the evaluation on your calculator correctly. Okay, so that's all I have for you today. Any question before we conclude our class? All right, so thank you, Rachel and Tristan, for being here with me today. If you have any questions, just let me know via email, okay? Have a great day, both of you.